Rubin platform is being described as a step change for AI systems. From a power and cooling perspective, why is this launch so significant, do you think, for data center design?
Well, Phil, that's a great question. When you're looking at NVIDIA Rubin and NVIDIA Rubin Ultra, we're looking at server racks that can exceed 100 kilowatts per rack, perhaps even go to 600 kilowatts per rack. In my opinion, that's a paradigm shift in data centers as we know it from the last decades, where traditional data centers are really focused on enterprise solutions that are 10, 20 kilowatts per rack at most. Now we're really shifting to new architectures with much higher power density, which require a different approach.
Okay, and there's a lot of discussion about AI driving what people see as unsustainable power demand. Do you see Rubin and similar platforms changing that narrative at all? And if that is the case, how, or are we heading for a possible crunch point?
I think there's two parts to that. I think Rubin and other kind of AI platforms are actually really efficient in how they manage a certain very large workload. I think the demand is really for really large workloads to be solved. And my job is to provide architecture solutions and technologies that can provide the solution to that in the most efficient way. So I wouldn't just necessarily put that on the hardware itself. I see that there's a generic, very large demand for AI infrastructure. I see how my kids do their homework. They use AI sometimes. I use AI daily. And I think it's a very useful tool for many people, and that needs to run on platforms. When you're looking at high density chipsets, it actually brings a lot of transistors closer together. So high density rack, a single high density rack, actually is more efficient than the same power in multiple diverse racks that are spaced further apart. And that's because the transistors have to also, during their AI calculations, do a communication step. And that communication step takes time and energy, and bringing them closer to each other actually allows for more efficient calculation. So we're actually focused on efficiency.
Okay, I think I'm right in saying that Eaton, you estimate up to 33% more AI factory output per grid connection. Can you explain what that means in practical terms for operators, who may well be facing grid constraints?
Yeah, so that leads to your previous point too. When you asked about, are we running into a challenge or a crunch point, right? When we see AI and the demand and some of the projections that are made, those are extremely large amounts of power that people project that are needed for these large AI plants. And currently, power and transmission and distribution are some of the bottlenecks to roll out AI hardware. So you look at power production, but also transmission and distribution. All the transformers and switchgear, all the stuff that Eaton makes needs to be developed for the data center. And when you look at the data center, what are the inefficiencies that are still left to be solved, right? One, we're trying to get, NVIDIA is doing their work to get the transistors to stick closer to each other. Other areas are the cooling system. The cooling system of a data center today can be as much as 40% of the energy bill. So when you're looking at grid and power being your bottleneck, do you really want to use 40% of that energy for the cooling hardware? There are approaches being championed by some industry leaders, and something that I've actually, in my prior role at the Department of Energy, have championed, is using hotter supply temperatures. The chips at their core run at 85 to 90 Celsius before they start throttling. And running the coolant today into a data centers, we do at somewhere around 30, 20, or 35 Celsius in that range. So there's a large temperature gap. When you're looking at data centers that go in the hundreds of megawatts, providing coolant at 20 or 30 Celsius, where outside it might be a very similar or even warmer temperature, requires a lot of energy for the cooling system. If I'm able to make advances at the cold plate design that allow me to put hotter coolant closer to the chip and still maintain the chip within its operating range, you can save a lot of energy at the cooling plant. And if you don't use that energy for cooling and instead use that for computing, you can gain perhaps up to 33% more output out of your AI factory for the same grid connection.
Okay, and you mentioned advanced cold plates there, and I guess those, along with the intelligent CDUs, are central to making what we might call, I guess, is it hot water cooling and viable. What's the role that sort of precision engineering plays in unlocking those efficiency gains?
Yeah, that's a great question. Traditionally, cooling for data centers includes fans and blowing a lot of air through a data center. When we switch to liquid cooling, standard liquid cooling solutions are, simple, long fin heat sinks. But we're seeing some advances coming where people are exploring multiple um, flow structures in 3 dimensions over the cold plate, still direct to chip, or other approaches that allow you to connect that fluid much more intimately with the chip. In order to do that well, which you asked, is sometimes the cold plate developers have to actually ask for the chip makers to give them the heat map of the chip. Where the hotspots, where's most of the heat going to come out? The heat fluxes at the surface of the chip are actually really high. They can be as much as 100 watts per centimeter square, and that is actually the same as a cooking plate in your oven or your stove. But I need to keep that silicon at a temperature, below 85 Celsius. So that's a tough engineering problem. And in the past, that was relatively disconnected. People build a chip and they put on a cold plate. In the future, we're seeing that engineered work really getting closer to each other and more focus on what they call the TCS loop, the technology cooling system, which includes the cold plate and the CDU, because that's an area, if you do the work right, you can save yourself putting down a big chiller plant.
Yeah, and perhaps sticking with that idea of collaboration, which you referenced there, how important is it to have coordination between cooling systems and electrical infrastructure when it comes to these next generation AI data centers? And maybe if you're happy to share, where do you think operators are perhaps falling short at the current time?
Um, I see it more like this, Phil, where in the past, the data center industry was really more of somebody builds a building, has real estate, then offers that up for lease and has a cooling system in the building. And then people rent that space and then put it in their server racks and then they cool with the air conditioners that are on the roof. That worked well for the telecom servers that do email, that do videos, that kind of light work. When we're talking 100 to 200 to 600 kilowatts per rack, the density, it's actually, I did the numbers to compare, are very similar to a car engine. So we're talking about an industrial block that just energy goes in, heat comes out. And that density of engineering requires both the power teams, the cooling teams, and the server teams to work together as one. And that to me is actually, if you think about the ways it's a little bit like the automotive industry or the aerospace industry, in which I worked before, where this is a co-engineered solution where you really have to make sure that that engine block of computing stays within its temperature limits and gives the reliability and performance that you expect. So to me, we're shifting from a telecom industry to an industrial computing sector, and that really requires that integrated approach. It's very unique that Eaton can do the end-to-end solution. We have the components from the grid all the way to the server. It includes the transformers, the switch gears, the UPS, the racks, the busways. All these elements are within the Eaton portfolio. We announced our intention to acquire Boyd Thermal, which gives us a cooling portfolio with cold plates and CDUs. So I look forward to really bring all these elements together, work with our server partners like NVIDIA and others, and truly make an end-to-end system, almost like a vehicle in which the chips can do their work.
Yeah, and I guess it's no secret that the AI workloads are accelerating the move towards liquid cooling, but be interested to know if you see this as a sort of niche solution for those hyperscale AI or gigawatt factories, as they're sometimes called, or do you think it's the beginning of a broader industry transition, or are we maybe, as we do in so many cases, end up in a hybrid world where there's a mix of solutions?
Oh, there certainly will be a hybrid world. There's no black and white in this, but that's I wouldn't call AI niche. That is a fun one. I had to
No, I
chuckle when
guess
you
at the
mentioned it.
hyperscale end, but yeah.
Even at there's many different workloads, so the system should be optimized for the workload that it does, and so should the cooling system. If the workload is above a certain power density per rack, you can see that the efficiency of a liquid cooled system will greatly outweigh an air cooled system when you go over 20, 30, 40, 50 kilowatts per rack, right? The amount of air you need to push at that point is very significant. Now, most workloads for telecom servers are not in those levels, so they can certainly remain air cooled. But when you go to high density loads, you want to do that liquid cooling. Now, the other question is, will in the future liquid cooling even be used for the other lower loads? And it could be. Maybe there's been initially some reservations in putting liquid into the data center. Maybe those issues get resolved, and the future of all data centers will be more focused on liquid cooling. That's just too hard to predict for me for now, but I do see that liquid cooling will mature even further as a technology and be easier to implement, and those will allow other servers to also be considered for liquid cooling.
And I mean, everyone at the moment is focusing on hyperscale AI factories and the large language models. But as I understand it, when inferencing comes along, or is beginning to anyway, and AI goes towards the edge, are we still looking at liquid cooling there, or is that possible that air cooling is good enough for those scenarios? Or
anything is always possible, but when you're looking at edge computing, maybe I can introduce that to the audience. Is that edge computing is a small local data center. You want sometimes for a data center to be more closer to you because the latency of interaction, the time of message exchange is lower, and therefore you can do inferencing, which is basically looking up a pre-solved problem into the AI tokenized space, can be done quicker because it can respond to you in a faster way. So what I envision then is seeing localized data centers. Depends a little bit on the local climate. If you are in a very cold environment, maybe air cooling is still just fine. If you want to, if that system sits in a very power constrained or in a very hot environment, you might want to go for liquid cooling, because liquid cooling does not only provide the ability to work with high density, it also allows you to do the same with less power from the grid because it's more efficient.
Thanks for that. And maybe in finishing, I think you said that the most exciting aspect of efficiency gains is they sort of align economics. So, there's some financial benefits along with sustainability. Do you think there's a way that alignment could reshape investment decisions in AI data centers over the next few years?
It's hard for me to make any predictions about investment decisions, but I can speak to the former a little bit more if you like. When Jensen Huang says that the cooling system doesn't contribute to tokens, he's correct. The cooling system is there to really provide the environment in which the chips can operate well. So we can find innovations on the cooling system, even also on the power system, to manage that energy flow in a more efficient way. That means that you're wasting less energy for processes that don't deliver economic value. And that can be quite substantial when we talk about the cooling system. The cooling system is necessary for the humans and for the servers in the room. And there always will be some level of cooling system, but it's also, I think, the area which is the richest area for gains in efficiency improvement, because it's a significant energy usage right now, and it's the one that doesn't contribute directly to the tokens process. So I'm excited, as at Eaton, to innovate in that space.
And maybe just finally, if I can ask, is I often ask folks, in terms of glass half full or half empty, we see the sort of predicted data center capacity going here and the power availability sort of here, and there appears to be an increasing gap. And as I understand it, it's because that's, if you like, reserved future planned data center capacity. So we haven't sort of come to the crunch yet. But do you foresee a major sort of bottleneck point, or do you think the work of companies like yourselves, working with server manufacturers, will mean that that gap never sort of gets out of control, should we say?
Well, projections are projections, what they are. They're not, the projections that I've seen, some of them are very, very big, and some of them are more modest. But the reality is this, Phil. some of the highest projections are 156 gigawatts installed by 2030. The amount of energy associated with 156 gigawatts is enormous. Even if half of that gets realized, even if 25% of that gets realized, that is an enormous market and build out. And I think the real challenge is not only the power production, but also, Eaton is extremely busy scaling up all of our production in transformers, in switchgear, and that it's a great business to be in, because the entire electricity grid globally is growing, and it's a sector that hasn't experienced this level of growth. And it's just the amount of equipment we can build, and the amount of power plants can be built, but also the amount of transmission and distribution technologies that we can provide while we're innovating the next generation of efficiency to make as most output per power produced as possible. That's what's all going on right now. So even if projections are here, if the projections are so extreme, it would require 10 Eatons to build all that equipment. If they are even reduced slightly, it doesn't matter. We're still very, very busy for a long time.
Oh, that's great. I mean, thank you so much for sharing some great insights into what's going on. Clearly, it's the AI world has kind of changed the rules when it comes to a lot of things in data centers. So, Peter, really appreciate your time. Thank you.
Thank you so much, Phil.